So what is quantum teleportation? Let's imagine again our favorite protagonists, Alice and Bob. Alice has a qubit in the state psi, which she wants to send to Bob. Unfortunately for them, there's no quantum communication channel between them. So how is there any hope of getting the qubit psi over to Bob? The answer lies in quantum teleportation. Alice will simply teleport the qubit. As you might imagine, this does not come for free. Alice and Bob need to share an entangled state, the EPR pair, ahead of time. Maybe Bob took qubit B with him when he departed from Alice on his journey, or in a more practically relevant scenario, the EPR pair may have been supplied to Alice and Bob by a complicated quantum network including quantum repeaters. Indeed, for building a quantum internet, the notion of quantum teleportation and sending qubits by teleportation is extremely important. Here, let's just say that they share the EPR pair. We will also let Alice send classical information to Bob. Two bits to be precise. Note that qubits cannot be sent over a classical channel, so this still doesn't solve our problem. We want teleportation to work even if Alice herself has no idea what the input qubit actually is. In other words, she has no classical description that she could send to Bob, no means to prepare psi herself. She's just given a qubit. So how does Alice teleport her qubit? Note that at the start, Alice has indeed two qubits. The one she wants to send, which I will call Q, and the qubit A, namely her half of the EPR pair shared with Bob. Alice now measures both Q and A together in a very special basis, namely the Bell basis. So what does this basis look like? One of the basis elements is the EPR pair. So note that here it's the EPR pair on Q and A. So on these two qubits here. All other elements of the Bell basis can be generated by applying Pauli X and Z operations to the A side of the EPR pair. I will hence label them using the bits A and B, and B, which indicate which Pauli operations we apply. So to be precise, 0, 0 means that we do nothing, just the identity. And this gives us the EPR pair. 0, 1 means that I apply this operation. So I just apply the Z, flipping the face, which gives me the minus. 1, 0 means that I just apply X, flipping the bit. And 1, 1 means that we do both things. Flip the face and flip the bit. You may want to convince yourself that these four vectors do indeed form an orthonormal basis for two qubits. So let's measure Q and A in that basis. The measurement outcome will be A and B, namely which of these Bell states Alice gets. What effect does this measurement have? As we will see shortly, if Alice got outcome AB, then Bob's qubit B is in this state, psi, namely the state that Alice wanted to teleport, and in front we have Pauli's X to the A and Z to the B. Of course, Bob does not yet know A and B. He would see a mixed state. In fact, you should convince yourself, having become experts in the quantum one-time pad, that indeed Bob cannot gain any information about Psi whatsoever at this stage. So teleportation certainly does not allow instantaneous communication. To be fair, Alice thus sends her measurement outcome, A and B, to Bob. Now Bob knows A and B and can decrypt Psi just as in the quantum one-time pad. So if n is the qubit that he holds, he applies XA to undo the X part, and ZB to undo the Z part. And we're just left with Psi. This is how quantum teleportation works. In the last part of this video, let's convince ourselves that all these claims which I've just made here really hold. So here I'm writing again the Bell basis. So what happens if Alice measures in the Bell basis? So we start with the state Psi on Q and the EPR pair shared between Alice and Bob. So let's take this state and let's rewrite it. And what I've done here is I've taken the state Psi and I've written out the qubit. So of course Psi is a qubit. It is described by amplitudes alpha and beta. So my goal is now to express this in terms of the Bell basis of Q and A. So if I do this, note that what I get here is A 0 0 0. I'll put the 1 over square root 2 in front, plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1. So let's try and rearrange this. And I'm claiming, and I'm not going to do the entire calculation here, but we'll convince ourselves that they are the same. I'm claiming that I can write this in the following way, namely, the Bell state 0 0 on Q and A tensor our original qubit plus on B plus phi 0 1 QA tensor psi on B with the Z applied to it plus 1 0 QA with the X applied to it plus phi 1 1 with X and Z applied to it. So to convince ourselves that this is true, up to some normalization we'll fill in shortly, is let me just take these guys and write them again out. So what I do is I have a 1 over square root 2 in front, because it appears in all the Bell states. And then what do I have here? I have from this part 0 0 0 times alpha plus beta 1 beta 0 0 1 plus 1 1 from the Bell state 0 times alpha plus 1, 1, 1 times beta. So this is just from this part over here. So let's now have a look at the second part, namely this one. So what do I get? I have from the Bell state, again, 0, 0, alpha times 0, 0, plus beta times 0, 0, 1. And I need to put a minus here because remember we put the z. Okay, so this here is a minus because z times psi is alpha 0 minus beta 1. Okay, very good. So we have the first part, namely the terms corresponding to this. Now come the term corresponding to this expression. And what we have is 1, 1 times the 0 part is alpha. And now we have minus with minus, so I get a plus, plus beta, 1, 1, 1. So you can maybe already see where this is going. So here I have alpha times 0, 0, 0. Here I have it again. Here I have beta 1, 1, 1. Here I have it again. But here I have this term occurs with a plus, and here with a minus, here with a plus, and here with a minus. So if we continue this calculation, we can cancel this term against this one, and this term with that one. Okay, let's now move on to considering the second part of this expression, namely these two terms. And something very similar will happen here. And to see that, let me first write out what is x applied to psi. So we have alpha, swap the bit, plus beta, 0. So let me expand this. So we have this Bell state here. So what do I have? I have alpha times 0, 1, 1 from here, plus 0, 1, 0 with beta. Now comes this portion, plus 0, 1, 1 with alpha, plus, and now we have this part with that part, 1, 0, 0 with beta. So this is what I get from here. So now let's do the last portion, namely this one, where I'll write here x times z on psi. So I start from here and I flip the bits, so what I get is alpha 1 minus beta 0. And you can probably guess what's going to happen now if I do this computation. So I'll start again now with this one. So what do I have? I have 0, 1 with 1, going with alpha, minus 0, 1, 0, going with beta, let's leave some space for myself in the video. So what do I have from this term? I have minus 1, 0, 1 with alpha. And now we have minus and minus, so I get plus beta 1, 0, 0. So let's have a look at this. What happens here? This term I have here and also there, so we keep that. What happens here? This term I have there and also there. And here we again have that this occurs with a plus here, and the minus here, the plus here, and with a minus there. So I can cancel this term against this one, and that term with this one over here. So what I'm left with is just these two terms. So if you look at them now, we can observe that this here, namely alpha 0, 0, 0, with beta 1, 1, 1, is precisely what we see here, alpha 0, 0, beta 1, 1, 1. So let's have a look at the second term. So now I have here alpha 0, 0, 1, alpha 0, 0, 1, which occurs here. And here I have beta 1, 0, 0, which was the term here. So you can see that if I now normalize this properly, we end up exactly with the same expression that we saw before. So you've now become an expert in quantum teleportation.